Hello, welcome to another video on how to solve some models in MATLAB. In this video, we are going to solve a similar problem that we solved before on packed bed reactor, where a reversible catalytic reaction occurs. But in this video, we are going to try out different models. We want to test the impact of different kinetic models on the performance of the reactor. So trying elementary model, the power law, the Langmuir-Aitken-Wood, and so on. So the model equations remain the same. So you have the mole balance, the energy balance, the pressure drop equation. We have the concentrations, the temperature dependent rate constants, and you have the different model. So this model one is the elementary one, then the model two is the power law, model three, Langmuir-Aitken-Wood, and so on. So these are the different models that we want to try out. We have similar initial conditions. So what we want to do is to check how the performance will change when we try to switch between one model, from one model to another, and then plot the profiles together. So let's see how we can do this in MATLAB. To define the parameters, so these are the parameters that we have in the model. So you define them, and then and these ones. And then the define the initial condition, because there are three differential equations. We have three initial conditions. T naught is the initial temperature that has been earlier defined here. And we have the catalyst weight, which is the range of our catalyst weight that we want to solve for from 0 to 20 kilograms. And then we have the labels, which is, this is basically the different laws that the different kinetic models that we want to try out. Okay, so now what we want to do is, we define your the model for a model equals to 1 from 1 to 5. Then we define the function that we want to run. So this is, we call the solver, and then we pass the reactor model, which will be defined later on. So similar to what we've done before. The only thing is that we have more parameters here. So these are additional parameters that you need to pass. And then this is the range that you want to run for, and this is the initial condition. So it's still the same thing. The only thing is that we have more parameters. So we expect the model to return this as output. Now the results will be stored in a variable result. So, and then we can grab, as we run for each model that we have here, it's going to grab, it's going to do for the first model, the second model, and then we'll assign whatever result that we obtained to W, and then for each model. So which means this W will contain will be a matrix instead of a vector this time, and the same thing for this for Y. Okay, and then we plot the result. So this is just to plot the results, and we plot it for the again for the different models starting from 1 to 5, and then we call the plot function each time, and we assign the model the number that matches the model we want to plot for. So we do the same thing, for the W and for the Y, and then we define, we say again we are plotting here. We are plotting the second the second variable. I think here concentration. This one, the previous one is temperature, and so on, depending on the order in which we specify things. So, okay, this is concentration profile. Here we just want to plot the concentration profile for the specific model 3, similar to what we did before. So here we just calculate the concentration again from the result that we've obtained here. So here we have extracted the result for model 3 in particular, and then we've calculated the concentration. Okay, and then we plot it. Now, after we've done all the scripting, Python we run that script, and then also we'll call the function within that script. So this is the function it's going to call, which is the reactor model. So this reactor model is the model that we're running here, the one that we pass to the solver. Yeah. So one thing similar to what I explained in my previous videos, the function has to be defined at the end of the file. So because that's how MATLAB runs the model. So it's going to call this model, but you need to place it at the end of the file. Okay, so this is the function. So remember what this means is a placeholder. So because we don't want to put W there. If you put W, it will work, but um, you might get a warning, and that's why we're using that placeholder. So again, we're extracting x, t, and y within that function because we need x, t, and y here. So that's why we're extracting them there. And then we are calculating those concentrations because we will need those concentrations subsequently in the model. So we need to use those concentrations here. This is where we are switching between the various model. So so if you do switch model, so for case one, so remember how we defined, one is from the first model, which is elementary model, is going to use that equation. If you switch to case two, it's going to use the second model, which is the power law. If you switch to case three, it's going to use the third model, which is the Lagrange in Sherwood, and so on. And then you end it. So then you define your differential equations and you return the xdw, dtw, and the ydw. Okay, that's what you always return the derivatives. Okay, so when you do that, so the key thing here is the fact that you need to, because you're trying out different model, you have to add an additional argument here as for model to show that you are switching between them. And then that model, we're specifying what those models are. So 1, 2, 3, 4, 5. And then here as well, you've defined that you're switching, that you are considering 5 different models, which you are assigning each time that we run the model. So this model is something that will be changing from 1 to 5 as we look through this model. So as we go from 1 to 5. Okay, so I hope that helps. So if we run it, what do we get? The results. So when we run it, yeah, we can generate the profile for the concentration, the temperature, the pressure, and then this is the one for model 3 that we did at the end. So just trying to plot the concentration only for that model. So which is the one we did here. Where is that? Yes, here. And that is the result for that. Okay. And you can see that most other models, they have similar behavior except for the power law. You can see that. I hope that helps, and I will see you in another video. Bye-bye.